Hello and welcome to Empowered Learning. This is the second video in the Logarithmic Differentiation series. And so now what we want to do is look at some examples to where in some instances we'll be taking the derivative of the equations that aren't necessarily functions or relations that aren't necessarily functions. And so because of that, we want to employ the steps that we talked about in the first video for logarithmic differentiation. If you do not recall those, we'll go back just a second to make sure that you understand why we're doing what we're doing here. So as we mentioned in the part one of this video series, whenever we had situations here, whenever we wanted to take the derivative of an equation, and that equation may not necessarily be a function, one of the things that we can do is follow this step process for logarithmic differentiation. So first step is just to take the natural log of both sides of that equation. And of course, I'm assuming here that this is a function, but the equation may not be representative of a function, but that's okay. As long as each term in the equation could be interpreted as a function, that's the requirement for us to be able to basically use the implicit differentiation. And thus, you would want to say, all right, I can just take natural log of both sides here. So I'll also mention that it does not matter if you do log base e or the natural log. You can do log of any base that you want. We just do natural log out of convenience. So after you do that, then of course you want to differentiate implicitly with respect to x or whatever other variable you have. And again, depending upon what you're told to take the derivative with respect to as far as a variable is concerned, that will dictate when you do the chain rule and when you don't do the chain rule, when you employ the implicit differentiation for each term in your equation. Of course, then after that, then it just turns into algebra, and you're basically trying to find out what the derivative of your function is with respect to whatever variable you were given. So that's the process that we're going to use here. All right, so looking at this particular equation here, we can kind of tell that this is not a function just because we have y is equal to x raised to the x. And so we don't have any differentiation rules here that allow us to be able to take the derivative of x raised to the x. Now we do have differentiation rules for taking, let's say, the derivative of x raised to the 2, or x raised to the negative 1/2, or even x raised to the square root of 2. We have differentiation rules for all of that, but we don't have it for what we see here. And so this is where we want to employ logarithmic differentiation. So we'll start off here by just taking the natural log of both sides. And then, of course, we know from our logarithmic properties that this particular exponent, x here, can be moved out in front. So here we have natural log of y is equal to x times natural log of x. And so now from there, we can take the derivative of both sides with respect to x, okay? So we'll go ahead and set this up. All right, so for our for our left side of our equation here, we see that the variables do not match, so we need to employ the chain rule. So the chain rule says I take the derivative of the outside function, which is derivative of natural log of y with respect to y, and that would just be 1 over y, times derivative of the inside function, which is just dy with respect to x. And since we do not, well, we do know, but we're acting like we don't know right now what y is implicitly, then we just write dy over dx. Now, in this case, we know what y is explicitly, but the thing is, we don't know how to take the derivative of that because that's the actual problem that we're doing. So that's why we just want to leave it as dy over dx at this point. Now, on the right side of this equation, we see that we have x times natural log of x, which we know those are two functions being multiplied times each other, so we'll use the product rule. So the product rule says that we'll take the derivative of the first times the second plus the first times derivative of the second. And of course, the derivative of x is just going to be 1, and the derivative of natural log of x is just going to be 1 over x. So as a result here, I'm also going to go ahead and rename this y prime and put it in prime notation since I'm done actually executing derivatives. So I have y prime divided by y, which is equal to natural log of x, because 1 times natural log of x is just natural log of x, plus x times 1 over x is just going to give me 1. And so from there, I need to find out what the derivative of y is. And I can do that just by multiplying both sides by y here. So this would be natural log of x plus 1, all that times y. And of course, we know what y is explicitly, so we'll go ahead and write it in now. And so that would be our derivative of y, which is equal to x raised to the x. So let's move on to the next example. So for this example, one of the things that we see here is that we could take the derivative of this by using a combination of the quotient rule and the chain rule. However, if you notice here, that would be a little involved. So what we want to do here to try to make things easier for ourselves is to exploit our logarithm properties. So what we can do here is, since y is equal to this, if we take the natural log of both sides here, and let me get this all written down. Then we know that on this right side here, we can use our logarithm properties to first take this exponent and put it out in front. So that'll be 1/4 times natural log of, and then of course division inside the logarithm we know means that we can do subtraction. So in other words, log base a of x divided by y is log base a of x minus log base a of y. And so if we use that property, then it ends up looking like this when we do it. Okay? And so from there, this turns out to be, relatively easy to do as far as derivatives are concerned. We'll go ahead and take the derivative of both sides with respect to x here. And we'll ignore the 1/4. It'll be dy over dx of natural log of x squared plus 1 minus natural log of x squared minus 1. And of course, on the left side here, just like how we did it in the last example, we know that the derivative of natural log of y with respect to x, variables don't match. So we do the chain rule. So the derivative of natural log of y with respect to y is 1 over y times derivative of y with respect to x is just dy over dx. And we'll call that y prime for short. On the right side here, when we take the derivative of this first term, we will be employing the chain rule because x squared plus 1 is the inside function. and natural log of blah is the outside function. So derivative of outside function with respect to blah is just 1 over blah, where blah is x plus 1, times derivative of the inside function. Okay? And then we'll repeat the process here for natural log of x squared minus 1. So x squared minus 1 is the blah, so derivative of natural log of blah is just 1 over blah, times derivative of blah with respect to x. And so if we now go back and take what is the derivative of x squared plus 1, we know derivative of x squared is just 2x, derivative of 1 is 0. So here all of this just ends up being 2x. And same deal here with x squared minus 1, the derivative of that is just 2x. And so you can see here that we have a common factor of 2x in both terms. So what I'm going to do is go ahead and factor that out. So if we do that, then this right side here will look like this. So it'll look like 2x over 4. And then this would be 1 over x squared plus 1 minus x squared minus 1, like that. So from here, this means that we have y squared, y prime divided by y, which is equal to x over 2, because 2 over 4 reduces to 1 over 2, times, and I'm going to make this a common denominator now. So to do that, I'm going to multiply numerator and denominator here by x squared minus 1, and numerator and denominator over here by x squared plus 1. So if I do that, that will be x squared minus 1 minus x squared plus 1. And then all of that will be over, and when I FOIL x squared plus 1, x squared minus 1, that'll be x to the 4th minus 1. And continuing on the right side, I know that if I distribute here, I'm going to have x squared minus 1 minus x squared minus 1 all over x to the 4th minus 1. And these x squareds cancel to 0. And I have negative 1 minus negative 1, which is a negative 2. So I have negative 2x over 2. All that over 1 over x to the 4th minus 1. And of course, that will just reduce to 1 and just be a minus x. So all of this is just minus x over x to the 4th minus 1. So with that being said, now we now know that y prime, which is just dy over dx, is just going to be this minus x over x to the 4th minus 1 times what our y was. And to do that, that will just be 4th root of x squared plus 1 divided by x squared minus 1. Okay. And so we could keep it that way, or we could, try to get a little more fancy and sort of break down what the 4th root of x squared plus 1 and x squared minus 1 is, because we know that we have a factor of x squared minus 1 inside of this x to the 4th minus 1, but I'm not going to do that here. So the purpose of this is just to show you how to get the derivative, and at this point it's just algebra, so we'll just leave this. All right, so for our next example here, this is an example of an equation where the equation is not a function, but we're assuming here that in this case, that y is going to be a function of x. So the variable y is a function. We just don't know explicitly what it is. So the best that we do know is that if we take the x root of both sides, if that makes any sense, then we know that y would be this. But the issue here again is that y is defined in terms of y. So that is what lets you know that y isn't necessarily a function. So, but we know that whatever it is written in terms of x, as we see here. And again, we have no specific rules for taking the derivative of something like this. If you wanted to write that in fractional exponent form, we have no rules for telling us how to take the derivative of a variable raised to the quotient of two other variables. So that's why we're going to employ logarithmic differentiation here. So to make this easy, we're going to take the natural log of both sides. And by taking the natural log of both sides, we can now exploit the logarithmic property here. I'll just leave that. Yeah, we want to exploit the logarithmic property here that says that anytime we have log of something raised to an exponent, we can pull those exponents out and multiply in front. So this will be y times natural log of x equals x times natural log of y. And so now from there, we want to find the derivative of y with respect to x. So now what we could do is actually take the derivative of both sides with respect to x. And so we'll go ahead and use Linus notation to do that. Pen got kind of stuck there. Okay, so therefore, if we take the derivative of the left side of the equation, we see here, again, we have y times natural log of x, which we're assuming that y is some expression of function in terms of x, and natural log of x is its own function. So here we'll be using the product rule. So use the product rule, we take the derivative of the first, with respect to x, times the second function, plus it's the first times the derivative of the second. And of course, second function is natural log of x. Derivative of natural log of x is just 1 over x. We do the same kind of thing on the right side. We take the derivative of the first, which is x. So the derivative of x is just 1 times natural log of y, plus x times the derivative of natural log of y with respect to x here will require that we end up using the chain rule. So I'll do that here. So now we know that for the chain rule, if we take the derivative of this, we know that the derivative of natural log of y is just 1 over y, times the derivative of the inside function y is just dy over dx. And of course, we're going to rename this y prime for short. So in essence, do the same thing here. This turns out to be y prime times natural log of x plus y divided by x, which is equal to natural log of y plus x times y prime over y. And so at this point, what we need to do is take every term that has y prime in it and algebraically manipulate our equation to have that on one side and have everything else on the other. So in here, I'm going to switch the way that this looks momentarily. Instead of dividing y prime by y, I'm going to move this over here and let the y prime be by itself. So we can do that. All right, so in doing this, I can subtract both sides by x divided by y times y prime. So when I do that, on the left side, I just have y prime times natural log of x minus xy times x divided by y times y prime equals. On the right side here, I have natural log of y, but over here, I still have this. So I want to subtract both sides by y divided by x. And so that leads me to this. So of course, from there, if I factor out a y prime out of both terms, I just have natural log of x minus x divided by y equals natural log of y minus y divided by x. And so now, if I divide both sides by this term here, then I'll have y prime, which is the same as dy over dx, is equal to natural log of y minus y divided by x over natural log of x minus x over y. And so you could leave it like this. One thing that I am going to do is multiply both the numerator and denominator by the LCD of both of our fractions here, which is just xy divided by xy. And if I did that, then of course this first term in the numerator would be x times y times natural log of y minus, of course, the x's are in common here, so they'll reduce to 1, and I'll just have y squared. And similarly, in the denominator, I will have xy times natural log of x. And here I have the y's that are in common in numerator and denominator, so they reduce to 1, and I just have x squared remaining. And so this is my final answer. Depending upon your instructor, this form may be also acceptable as well. So looking at our next example, we want to take the derivative of y with respect to x for our function, which is log base 6 of x plus 4 divided by x minus 4, all that raised to the natural log of 6 power. And so if we look here, again, you'll see that we have a function to where it's written logarithmically, and inside of it, we can actually use our logarithm properties to rewrite how it looks. So that's actually what we're going to do first, to try to make doing the derivative of each term easier. So the first thing that we see is that we can take this natural log of 6 and move it out in front. Multiply, so we have natural log, that didn't look so hot, so let's try that again. So we got natural log of 6 here, of course, saying earlier we can move that out in front. And so that'll be log base 6 of x plus 4 divided by x minus 4. And of course, the division of logarithm on the inside means that you can have subtraction on the outside. So this will be log base 6 of x plus 4 minus log base 6 of x minus 4. And so what we would be taking is the derivative of what we see here, which is way more simple than what we would have had to do if we would have kept everything in this current form. So now the derivative of y with respect to x, natural log of 6 is just a constant, so we just ignore that. And so now what we want to do is take the derivative of each of these terms separately. So log base 6 of x plus 4 minus derivative of log base 6 of x minus 4. All right, so for the derivative of log base 6 of x plus 4, again, this is a composition function because x plus 4 is the inside function, and log base 6 of blah, where blah is x plus 4, is the outside function. Sorry, yeah, it's the outside function. So when we take the derivative of log base 6 of blah, that's just 1 over blah, which is just x plus 4 times natural log of 6 times now the inside function times the derivative of the inside function, and of course the derivative of x plus 4 itself would just be 1. Minus, and we repeat the process here, so derivative of the outside function, log base 6 of blah, is just 1 over blah times natural log of 6. And then that's times the derivative of x minus 4, which again we know is just 1. So we have a common factor of natural log of 6 in the denominator of both of our terms. So what we're going to do here is just factor that out. And what we have left is 1 over x plus 4 minus 1 over x minus 4. And of course the natural log of 6 is reduced to 1. And our derivative here just ends up being 1 over x plus 4 minus 1 over x minus 4. And we'll just rewrite that as one quotient. And so we'll multiply numerator and denominator by x minus 4 in the first term and x plus 4 in the second term. And if we do that, we end up getting the following here. And again, x plus 4 times x minus 4 is the LCD, which is x squared minus 16 when we follow it out. We distribute here. We have x minus 4 minus x minus 4. And we see that we have these x and minus x terms cancel. And we'll see at the end of the day here that minus 4 and minus 4 is minus 8. All of that over x squared minus 16. And that will be our derivative here. So of course our y prime just ends up being negative 8 divided by x squared minus 16. And so for our last example, this one I have worked out, but you see that we have a lot going on with it. And we're asked to take the derivative of y is equal to x times square root of x squared plus 5, all that over x plus 6 raised to the 2/3 power. And so if we were going to take the derivative of this straight up by using the quotient rule, you'll end up seeing that in using the quotient rule, we would use the chain rule within the quotient rule. And again, it's not impossible. It's just that if we exploit our logarithmic properties, we can take the derivative of each term once we rewrite this much easier than what we would have to deal with if we did the combination of the quotient rule and the chain rule to do this. So first thing that we do is just take the natural log of both sides here. And so when you do that, you see that's what we have here. I've also changed square root of x squared plus 5 to just x squared plus 5, all that raised to the 1/2. And then of course, using our logarithmic properties, we know that anytime we have log of something divided by log of something else, log of something divided by something else, where we have a quotient inside the logarithm, we can rewrite that as, in this case, natural log of numerator minus natural log of the denominator. So that's what you see here. from this moment, we notice that we have multiplication inside the first term. So we could rewrite natural log of x times x squared plus 5 raised to the 1/2 as just natural log of x plus natural log of x squared plus 5 raised to the 1/2. Okay, and then similarly, we could take this exponent and pull it out via our logarithm properties. And thus, we could take this 1/2 and also pull it out. And from that, you see that you end up having this result. So we know that natural log of y would just be what we have here. And now what we want to do is take the derivative of that. So we scroll on down, we'll see that taking the derivative of both sides of this equation with respect to x, of course, the right side is going to be not much of a problem, because one of the things that you see is that for every term that our variables match with whatever we need to take the derivative with respect to, so that's easy. For here, the derivative of natural log of y with respect to x, we've done this several times, so we know that we end up with this result. Derivative of natural log of x is just 1 over x. Derivative of, what is this, there's something that's not supposed to be written there, so let me go ahead and write this in. This is supposed to be natural log here, but got written out. So anyway, derivative of natural log of x squared plus 5 is just 1 over x squared plus 5 times the derivative of the inside function there, which is just 2x. Okay, so that's just 2x. And of course, same deal here, using the chain rule, the derivative of natural log of blah is just 1 over blah, where blah is x plus 6, times derivative of x plus 6, which is just 1. And so you see the 2x that we had in that second term is here. And from this point, see that we have all of this, and we just try to simplify as much as we can. And of course, we see that these 2's here reduce to 1. And so then from that point, we're just in a matter of rewriting everything after we multiply both sides of our final equation here by y. So if we took this and multiplied by y, then that would be the same deal here. And of course, we were given what y was in the beginning, which was all of this. So now all we're doing is taking what we have here and just throwing in what y was explicit. And of course, we could stop there. And so this concludes the video series on logarithmic differentiation. I hope that this helped. If there's any other examples that you may want to see, or any clarifications to things I did in this video, just please comment, and I'll get to you as soon as I can. Thanks.